a long-standing particle physics hypothesis comes to an end. For decades, physicists have speculated that a mysterious particle, the sterile neutrino, might resolve some of the most perplexing inconsistencies in neutrino physics. New results from the MicroBooNE experiment at Fermilab now show that this particle does not exist, closing a major chapter in the field and redirecting the search for new physics. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video with your friends and colleagues. Using high-precision measurements, the MicroBooNE collaboration found that neutrinos behave exactly as predicted by models containing only the 3 known neutrino types. There was no evidence for a hidden fourth neutrino state. While this outcome rules out one of the most popular explanations for earlier experimental anomalies, it represents a decisive advance. It narrows the range of viable theories and provides a firm foundation for future experiments, including the ambitious Deep Underground Neutrino experiment, DUNE. The findings, published in Nature, significantly constrain explanations for puzzling neutrino observations that have challenged physicists since the late 20th century. Why neutrinos challenge the standard model? Neutrinos are among the most abundant particles in the universe, yet they are notoriously difficult to study because they interact only weakly with matter. Within the standard model of particle physics, a remarkably successful framework, neutrinos were originally assumed to be massless. That assumption was overturned when experiments detected neutrinos changing their flavor as they traveled through space. This phenomenon, known as neutrino oscillation, can occur only if neutrinos possess mass, something the standard model does not naturally explain. As a result, neutrinos remain one of the clearest indicators that the standard model is incomplete, alongside unresolved problems such as dark matter, dark energy, and gravity. The rise of the sterile neutrino hypothesis. In the 1990s and early 2000s, experiments at Los Alamos, LSND, and later at Fermilab, MicroBooNE, reported results that could not be explained by oscillations among the 3 known neutrino flavors alone. In particular, they observed an unexpected appearance of electron neutrinos from muon neutrino beams. To explain these anomalies, physicists proposed the existence of a sterile neutrino, a hypothetical particle that would not interact via the electroweak force, making it invisible to conventional detectors. Although difficult to detect directly, such a particle could influence oscillation patterns, offering a seemingly elegant solution. For nearly 30 years, this idea dominated theoretical discussions. How MicroBooNE put the theory to the test. MicroBooNE was designed specifically to scrutinize these anomalies with unprecedented detail. Operating between 2015 and 2021, the experiment used a liquid argon time projection chamber to record neutrino interactions from Fermilab's neutrino beams with exceptional spatial resolution. The strategy was straightforward but powerful. If sterile neutrinos existed, muon neutrinos should oscillate into electron neutrinos at rates exceeding standard predictions. By comparing observed electron neutrino counts with theoretical models, both with and without sterile neutrinos, the team searched for any statistically significant excess. No such excess was found. Instead, the data were fully consistent with the 3 neutrino framework. This result reinforced earlier findings published in physical review letters and decisively ruled out the sterile neutrino as an explanation for the observed anomalies. A shift in perspective for neutrino physics. While the sterile neutrino hypothesis has been eliminated, the original experimental anomalies remain unexplained. This has prompted what researchers describe as a paradigm shift. With a long-favored idea no longer viable, scientists are now exploring a wider range of possibilities, including alternative particle interactions, detector effects, and more exotic new physics scenarios. One promising direction involves re-examining whether photons were misidentified as electrons in earlier experiments, an effect that could mimic neutrino signals. Ongoing analyses within Fermilab's short baseline neutrino program aim to clarify these possibilities using improved detectors and analytical techniques refined by MicroBooNE. Preparing for the next generation, DUNE. At the same time, the field is looking ahead to DUNE, the largest and most ambitious neutrino experiment ever undertaken. Located deep underground in South Dakota and connected to Fermilab by an 800-mile neutrino beam, DUNE will operate on a vastly larger scale than MicroBooNE. With its unprecedented sensitivity, DUNE is expected to address fundamental questions about neutrino masses, matter-antimatter asymmetry, and possibly the origins of the universe itself. The success of MicroBooNE has been crucial in preparing scientists for this next step, validating both the detector technology and the analytical methods required for such precision measurements. Conclusion: the sterile neutrino was once seen as a particle that could explain everything. Its absence, confirmed by MicroBooNE, is not a setback, but a clarification. By ruling out a major theoretical detour, physicists have sharpened their focus and strengthened the experimental foundation of the field. The mystery of neutrinos is far from solved, but it is now better defined and the path forward is clearer than